All right, in this video lesson, we're going to learn about the equilibrium law. Now, in this lesson, you are probably going to want to just pause every so often to make sure that you've got copied down into your notes the note that I'm going to talk about here. So the equilibrium law says that the ratio of equilibrium concentrations of the product to reactants remains the same no matter what initial concentrations were mixed. So it doesn't matter what you start with, the ratio of concentrations of reactant to product is going to always be the same for a reaction. If you start with no product and all reactant, you're going to end up with the same ratio as if you started with all product and no reactant, or a little bit of both. So the ratio of concentrations of reactants to products is called the equilibrium constant, and it has this symbol, K with a subscript EQ, so K equilibrium. And we can calculate the K equilibrium mathematically. So to do that, we're going to look at a fake example where we have A plus B is in an equilibrium with C plus D. And all of them have a coefficient in the light blue color. That's their small letters. So there is small letter A amount of big A in the equilibrium. So to calculate K equilibrium mathematically, you write it out like this. The concentration of the products to the exponent of their coefficient is divided by the concentration of reactants to the exponent of their coefficients. So you are taking the concentrations at equilibrium, and then you are pulling their coefficient down from the balanced chemical equation and putting it as their exponent. So you're using concentrations at equilibrium, and exponents are the coefficients from a balanced chemical equation. When you write it out like this, K equilibrium equals concentration of C to the exponent C times concentration of D to exponent D divided by concentration of A to exponent A times concentration of B to exponent B, that whole thing in the pink box, that's called an equilibrium expression. So determining equilibrium expression is very straightforward. So we're just going to look at getting the equilibrium expression for the synthesis of ammonia. So in this reaction, we have nitrogen gas plus hydrogen gas in an equilibrium with NH3. So therefore, we write our equilibrium expression. K equilibrium is equals concentration of NH3, so products, to the exponent of the 2, because there was 2 moles of that NH3 in the equilibrium from the balanced chemical equation, and then concentration of nitrogen gas to no exponent because it's an invisible 1, times concentration of hydrogen gas to the exponent 3, because there's 3 moles of hydrogen in the balanced chemical equation. So that's it. That is the equilibrium expression. It tells us the ratio of concentration at equilibrium. So then you can really easily solve for K equilibrium if you have concentration values. So I'm going to tell you that we have the concentration of NH3 EQ, so that means at equilibrium equals 3.1 times 10 to negative 2 mole per liter. Nitrogen gas concentration at EQ, so at equilibrium, equals 8.5 times 10 to negative 1 mole per liter. And concentration of hydrogen gas at equilibrium, 3.1 times 10 to negative 3 mole per liter. So to solve for K equilibrium, you just have to substitute in these concentration values at equilibrium. So it's always the concentration at equilibrium that is used to calculate K equilibrium. And I just want to note here that this K equilibrium is completely unrelated to the K constant in reaction rate. completely unrelated. So if you substitute in your values, you've kept your exponents as coefficients, your equilibrium constant calculation looks like this. And then if you do the math, you get something that looks like this. Now, our units for K equilibrium, you can obviously go through and prove that the units for this example is L2 L squared per mole squared. We're going to talk about units for K equilibrium in a few minutes. So this equilibrium constant, K equilibrium, equals 3.8 times 10 to the 4 liter squared per mole squared, is the equilibrium constant for the synthesis of ammonia. So now we're going to look at calculating the K equilibrium for the decomposition of NH3. So now we're going this way, 2NH3 gas in equilibrium with nitrogen gas plus 3H2. So we're basically looking at the reverse reaction. So now it's going to be flipped because now these are the products, so they go on top, and this is a reactant, so it comes on the bottom. Because we're calculating it for the decomposition of NH3, we put a little 1 up here in superscript because that's indicating that we're now calculating an equilibrium constant for a reverse reaction. So again, we can sub in our values and we keep that little mark here, that's superscript 1, and we calculate it out and we get 2.6 times 10 to the negative 5. So just remember that an equilibrium constant expression, so right here, our equilibrium expression right here, is actually just the opposite, flipped upside down for its reverse, so it's reciprocal. And it's shown just right here. So K equilibrium over 1 equals 1 over K prime equilibrium. So the little tick right here, it means prime. Or we can say that our K equilibrium prime equals 1 over K equilibrium. It's just saying that they are reciprocals from each other. So before I give you some practice, I just want to talk to you about a couple rules for our equilibrium. So the first rule is that K equilibrium depends on temperature. So if the temperature changes, the equilibrium expression is also going to change because we know that rates and reactions are temperature specific. The equilibrium expression for the reverse reaction is a reciprocal of that of the forward reaction. So we've already seen that. We've already seen that they're reciprocal or basically flipped upside down from each other. Our third point says that the units of K depend on the reaction. If we use concentrations in mole per liter or molar, we don't need to write units. So as long as you are using concentrations in mole per liter to calculate your K equilibrium, you do not need to include units. That's a big one because figuring out the units is a big pain in the butt when you're dealing with exponents. The fourth rule for K equilibrium is the value of K equilibrium for a reaction at a specific temperature is the same no matter the initial concentrations. So I've already talked about that. And then the final rule is solids and liquids are not included in the equilibrium expression. And that's a big rule because you should just always remember never to include solids and liquids in an equilibrium concentration. So to do some practice, I have some right here for you. You're going to go page 442, number 1, 444, 2 to 6, and 447, number 7. And I will do a couple of these equilibrium expression questions with you in class. That's it.